Welcome to The Explainer. Today we're pulling back the curtain on the engineering secret that has turned building massive AI models from a wild art form into a predictable science. We're talking about a set of rules that lets labs kind of see into the future of their own creations. These are scaling laws.
Okay, so let's do a little thought experiment. Imagine you're running a top AI lab. You've got $1 billion, a warehouse full of the best computer chips, and one mission: build the world's best AI. But with all that pressure and a million different choices, how do you even start? How do you make sure you don't just set $1 billion on fire?
Not that long ago, this whole thing was a massive gamble. The old way was just go big. Pour all your money into training one gigantic model, cross your fingers, and just hope it worked. But now, there's a much smarter, more scientific way to do it. One that's all about spending a little to learn a lot so you can predict what's going to happen when you go big.
And the answer to that billion-dollar question? It all comes down to this incredibly powerful idea called scaling laws. This is the playbook, the secret formula that lets engineers build new and better things instead of just copying what everyone else has already done.
So what in the world is a scaling law? Well, you can think of it like a cheat code for building AI. It's a surprisingly simple mathematical rule that tells you with amazing accuracy how much better your model will get if you give it more data to learn from, make it bigger, or just throw more computing power at it.
Yeah, this predictability is a total game changer. It means you can actually calculate your return on investment. If you put in this much more data, you can expect to get this much more performance back out. And that turns these huge, risky bets into smart, calculated decisions. It stops labs from wasting millions going down dead-end paths.
But here's the thing that's really fascinating to me. This isn't some brand new, out-of-the-blue discovery. The core idea behind scaling laws has actually been around for decades, long before the AI boom we're seeing right now.
As you can see on this timeline, the seeds were planted way back in 1993 at Bell Labs. And then, over the years, researchers kept building on this idea, getting closer and closer, until 2020, when OpenAI finally codified these laws for the transformer models we use today. And that's what really kicked off the race we're in now. A really key moment was in 2017. A paper from Hessness and his colleagues identified what they called the power law region. It's this sweet spot where as you add more data or compute, the model's performance gets better in this perfect, predictable, straight-line way. Nailing down that predictable region was the key to being able to forecast how these models would behave at scales no one had ever tested before.
Okay, so that's the theory. But how do engineers actually use this stuff to make those huge billion-dollar decisions in the real world? Let's get into the playbook they use to build better, more efficient AI.
One of the first big questions you have to answer is, what kind of model are you even going to build? What's the architecture going to be? Do you go with something new like a transformer or an older design like an LSTM? Scaling laws give you a data-driven shortcut to the right answer without having to spend a fortune building both just to see which one works better.
So what you do is you train tiny little versions of each one and just compare how they do. And as this chart shows, that's exactly what researchers did. They found this huge consistent efficiency gap. The transformer architecture was just fundamentally better at using compute, and that advantage held up no matter how big or small the models were.
All right, so this brings us to probably the most important question of all. If you have a fixed amount of computing power to spend, what's the best way to use it? Do you build a smaller, more focused model and train it on a massive amount of data? Or do you build a gigantic model and train it on a smaller dataset?
And for a while, that was a really tough call. But then, in 2022, a huge paper from DeepMind came out. Everyone calls it the Chinchilla paper, and it offered a shockingly simple and elegant answer to this exact problem. It was a rule of thumb that basically changed how the entire industry thought about this trade-off. The huge insight from that Chinchilla paper, it boils down to a single ratio, 20-to-1. They discovered that for the best performance, the sweet spot is to have about 20 data tokens for every one parameter in your model. And a token is just a piece of a word, and a parameter is like a little internal knob the model can tune. So 20 word pieces for every one knob? Simple as that.
Honestly, this finding was a bombshell. It meant that a lot of the biggest, most famous models out there, like GPT-3, were actually undertrained. They were these massive, powerful brains that had been starved of data. The whole industry had been obsessed with making models bigger, and Chinchilla came along and proved that what really mattered was a better balance, with way more emphasis on data.
So, with that huge insight from Chinchilla about what to aim for, that data-to-parameter ratio, engineers could finally perfect the how.
And it all comes down to this super elegant 4-step process you see here. You train a few small models, you plot their results to make sure you see that predictable straight line, you extend that line out to predict how your giant model will do, and then you build it, just once, with confidence.
But, and this is really important, we have to remember that scaling laws aren't a crystal ball. They are incredibly powerful for predicting some things, for sure. But the map they give us, well, it definitely has some blurry spots and uncharted territory.
Here's what they're amazing at: predicting a model's training loss. That's really just a score of how many mistakes the model makes while it's learning its main job, like predicting the next word in a sentence. The lower the score, the better. And when you plot that score against compute, you get that beautiful, predictable straight line.
But the moment you start trying to predict how well the model will do on some other more specific task, like passing a medical exam, things get way less certain. You also get these bizarre emergent abilities that seem to just pop out of nowhere. And even weirder, sometimes you see inverse scaling, where models actually get worse at something as they get bigger. It's wild.
In this quote right here, it gets to the very heart of why that happens. The further a task is from what the model was originally trained on, from its distribution, the less reliable those scaling predictions become. If a certain skill wasn't deeply embedded in the training data, then really, all bets are off. You can get all sorts of strange results that the laws just can't see coming.
So it's pretty incredible, right? Scaling laws have given us this clear, predictable roadmap for making AI better and better. We can literally chart its progress, but that same roadmap also shows a potential dead end on the horizon. These models need more and more high-quality data. So it leaves us with this massive, critical question for the future of AI. What happens when we run out?